Yeah.
Good afternoon. Welcome back to the APRG seminar. Today our speaker is Rajula Srivastava from Hausdorff Center, University of Bonn, Max Planck Institute, Germany. So she shall be talking on counting rational points near flat hypersurfaces. So I request her to give the talk, and I also request all the audiences to mute their microphone and turn off their camera. And over to you, Rajula, so you can talk.
Thank you, Mona, for the introduction and for the invitation to both you and Professor Curry. It's really nice to be back, as I said, whether online or in person. And I'm happy to be able to share some new work with you guys. So yes, today I'm going to talk about counting rational points near flat hypersurfaces. And this is based on joint work with Nicholas Technau, who is also a postdoc at Bonn. And so let's start. So as I guess you can probably tell from the title of the talk, it sounds very number theoretic, right? But hopefully the theme of this talk and my aim to this talk is to show you something which I was very pleasantly surprised to see, that given a counting problem, especially related to inequalities, counting solutions to inequalities, there is often harmonic analysis lurking right under the surface, which is super nice. And maybe an example which some of you might have heard about was the proof of the Vinogradov's mean value theorem using decoupling, which was a big breakthrough in harmonic analysis a decade or so ago. But today we'll not be talking about decoupling or Vinogradov mean value theorem. We will be looking at a different kind of counting problem involving Diophantine inequalities. And as you will see, we will start by stating the number theory problem, discussing some geometry, but by and by you'll see how we descend into harmonic analysis, and underlying is a lot of oscillatory integral theory. So let's start by stating the problem. So what I want to do is I'm an Rn, that's n is my dimension. I have a hypersurface there, a compact one. And suppose it has a nice parametrization. So it's parameterized at least locally by a smooth function f. So f is a function from Rn to R. And just to make everything simple, it's compact. So let's say, suppose it's parameterized over the n-1 dimensional cube, right? Or you can take your favorite compact domain. It's okay. So the question we want to answer today is, or understand, is this. So given this nice manifold in Rn and the hypersurface, how many rational points with denominator of a certain given dyadic size are present in a small neighborhood of this hypersurface? Okay. So now here, when I'm asking this question, there are things which I need to quantify now. So I say rational points, which are fractions in Rn of the same denominator. So I will have to first make precise what I mean by the dyadic size of the denominator, which would be denoted by the parameter big Q. And then also when I say a small neighborhood of my hypersurface, I have to quantify how near I'm getting to the hypersurface. And for that, I have another parameter delta. So delta measures how near you get to your hypersurface when you're counting these rational points. And Q measures the size of the denominator. And we are not looking at just a single denominator. That's important. We vary our denominator at least over a dyadic interval, which gives you this additional averaging in this extra variable as well. And just a bit of a small thing, so you don't really need to worry about it. So instead of delta, the distance that I'm taking from my hypersurface is actually delta over Q, and that is just for normalization purposes. It's just nice when you clear denominators, and it doesn't really affect anything because the range of delta just gets modified accordingly, right? So this is what I'm trying to count. So these are fractions. So whenever you see a bold font letter here, that will always denote a vector. So this is a fraction in n-dimensional fraction with denominator q. The size of the denominator varies between is roughly of size big Q. And the distance of these fractions from my hypersurface is less than delta over Q. But this is right now, this condition, which is the most important one, is stated in terms of my hypersurface. But this is the parameterization I have chosen. So let's reformulate this counting function in terms of the function that I have, because that's what I would actually work with. So so I've reformulated this function over here, and there are three conditions. So let's see. The first one, so now basically when I'm looking at a hypersurface, the idea is my first n-1 coordinates are free. I can choose them. So that's why here, this is for the, now I'm looking at the first n-1 coordinates. So I have a rational fraction, I have a rational number of dimension n-1, okay? And then because I know that my hypersurface is parameterized by f, that's how the last coordinate should look like, f evaluated at the first n-1 coordinates. So, but I want the last coordinate to be a rational with the same denominator q as well. So the third condition is just saying, I'm reformulating this nearness to the hypersurface by saying that, okay, if I let my first n-1 coordinates run free in rationals, but I plug it, the last coordinate would be f, the function f plugged with those n-1 coordinates plugged in. How far is that last coordinate away from being a rational with the same denominator as well? Which is what this last condition is measuring. And that has to be less than delta over q, because that's the amount of nearness I want. So you look at, I mean, the across all integers or all fractions, this distance should be less than delta over q. So this is just the reformulation we'll be working at. The second condition is again just saying that the denominator is diagonally of size q. And the first condition is saying that the numerators are bounded by the denominator, the size of the numerator, which is just because I'm parameterizing my surface over the unit cube. So it has to lie in the unit cube, that's it. Okay.
So here, Rajula, I have a question.
Yeah.
Q, this is symbol, this tilde Q.
Yeah.
What does that mean?
That's a good question. Yeah, I'm being a bit like offhand about it. Yes, here I don't mean asymptotically. I mean it is equivalent of size. So basically Q small. Basically, what is written over here essentially, right? So Q
Okay,
is of size. Yeah. That's I just had less space. Yeah, but yeah, not asymptotic. Thanks. Other question? Okay, and then you can just clear. So you can just clear the denominators over here in this condition, which is where the delta over q normalization is helpful. And then this condition can be reformulated in terms of the distance to nearest integer of q times f of p over q. So this is now the counting function we would work at in terms of my parameterizing function f. And you don't have to keep it in mind. I'll keep reminding you of the definition of this function. But now the question is, what does harmonic analysis got to do with it? And as I want to show quite a lot. But before delving into all of that, let's try to see first what is
I will again skip the clarification. What is this thing? Q into f of p by q norm r by z means what is that?
Yeah, this is to the nearest integer. So minimum over all integers. Basically this condition, but you multiply throughout by q. So
okay. I understand. Okay. So q f p by q minus m, right?
Minus m, and then you take an infimum or minimum. Yeah. Okay. So thank you for the clarification. It's nice to keep. So you have the definition right here. So first, before trying to prove something or formulating a conjecture, we should first try to get some heuristic idea to feel for this function, like what is the kind of answer we should expect, right? So let's see. There are three conditions here in the definition of this counting function. The third one obviously is the most important one. But for a moment, let's just forget about this third condition. So I kind of forget about this one. So then, and let's see if then what am I counting, which would obviously be a very bad answer, but it's a starting point. So then this condition is just saying you count all fractions of denominator of roughly size q, big Q, and the numerators also go up to big Q. So you have q to the power n many choices, sorry, q to the power n minus 1 many choices for the numerator, and then same q many choices for the denominator. So if you would pretty much count everything without really wondering about how close you are to your hypersurface, then this is what you would get, which obviously is not an interesting, and it's also not a very wasteful count. So, but this is something which is there. But although it's wasteful, there is an example of a hypersurface for which this is actually the best you can do, which is, for example, if you think about a hyperplane, which is say parallel to the one of the coordinate planes, right? So then what would happen is it won't really matter how close you get to your plane. It's totally aligned with the lattice of your rational points. So you can actually see that in fact, you would be able to get as many as q to the power n points lying on the plane itself. So it doesn't really matter how far or near you are. You catch everything, and that's because it's perfectly aligned with these lattices that you're counting at, right? And that what is saying, I mean, what the purpose of this example is to show you that the geometry is really important, especially if you're counting things around your surface, because and flatness is kind of an enemy if you want to prove some better estimates over here. And this is an enemy which keeps cropping up in harmonic analysis as well. Curvature is very important to us. So that's, I mean, kind of an indication about why harmonic analysis could be useful in some sense, a very important indication, but yeah.
No, actually,
okay.
I missed this point. Could you please repeat this thing?
This third one, this one?
So when M is a hyperplane and this part is what?
And
M is hyperplane?
Plane, what you can do is, I mean, think of like the last quarter being 0, right? So pretty much all the points that you count will either become third condition when it's 0 doesn't really mean anything. The third condition. Yeah. So you will really count as many points. The delta thing doesn't play any role because it's all 0 anyways. So that's pretty much, and geometrically how you see it is like it's lying completely flat, and your rational points, they actually form a lattice, right? So they will really, the plane will really align with this, and it will actually catch all the rational points that you have. That's pretty much the idea. Geometrically, and if you think a bit about it, you'll see that this is what's going on. Okay. So I mean, the intuition I want to give from here is, if your hypersurface is curvy, it has more of a chance to miss these rational points, and you can hope to get something better depending on how close you are to your hypersurface or not. Flat. So, but in order to prove like a nice general theorem, you have to disallow for these kind of flat, completely flat cases. So your hypersurface needs to be non-degenerate in some sense, and I've kept it in quotes because it's vague. We don't really know even now what's the, a characterizing condition where you can prove a really nice theorem for hypersurfaces. Today we'll see one such nice class of surfaces where you can. But yeah, but what I'm saying is that you have to somehow disallow for some flatness. Now, to what degree, that's a question. Anyway, so okay, suppose so what's a better conjecture that we should think about for this kind of a problem? So if everything was nice and random, and if I look at the third condition, that's saying that you are kind of cutting out a neighborhood of radius delta around your hypersurface. So if everything is behaves randomly, then I would expect that, okay, if the total number of points that we saw that we can catch is q to the power n, but if things are random and I'm in a delta neighborhood around the surface, I should only catch a delta proportion of the points that I would otherwise get. And that's why a good guess for a non-degenerate hypersurface would be, okay, probabilistically speaking, there should be delta times q to the power n many points of these kind in a delta neighborhood of my hypersurface, as a guess. But this heuristic also cannot always be true, no matter what your surface is, because imagine if this was true for some nice surface. What this is saying is, what happens when delta equals 0? This, what you have on the left right hand side, is obviously 0. So what this would say, if this were true, is that on your hypersurface, you can predict, like on your hypersurface, there are no rational points at all. And that is not really true. I mean, you can't really, when it comes to counting points right at a hypersurface, things are way more dependent on the algebraic nature of the hypersurface as well. So you cannot really just use geometry and say, oh, for this class of surfaces, there are no rational points on it. So what that means is, okay, maybe this is a nice term which does predict how many points you should catch for some range of delta. But once delta gets small, I should have another term which might tell you how much points you might find on the hypersurface itself. And it seems like a good guess for that term, for points on the hypersurface, is q to the power n minus 1. So one more dimension less. And this kind of guess comes from actual counting points. So for example, in the plane, you can think of the parabola, which does have these many points on the plane. You can count by actually counting it. Or, for example, on spheres in Rn also, you actually find these many points, and that's not a trivial fact. You have to use Hardy Littlewood method to actually figure this out. So, but the point is, some kind of correction term is needed, and it seems this is a good term for that. So then we have two regimes. When we are kind of away from the manifold, when our delta is large enough, we know that this term over here should be our should be the dominating one. But a bit nearer, when you get very near to your hypersurface, q to the power n minus 1 is a good count. And then you can play the game and see pretty much when does the first term dominate over the second. You just equate it, and it dominates precisely, the first one dominates precisely when delta is bigger than q inverse. And you maybe take an epsilon of room, that's better. So basically then what the conjecture we would like to prove is, suppose we have a compact hypersurface M, which is non-degenerate in some sense, then at least for delta bigger than Q inverse, so we are sufficiently away from the hypersurface, this should be a guess for the hypersurface, for the count, rational point count around in a delta neighborhood of the hypersurface. I do mean it, I mean here the tilde is again not well defined, but I mean it in an asymptotic sense, but with constants which could depend, which will depend on the manifold. I mean, at least that's what we'd like to find out. So that's the conjecture that we would like to prove for sufficiently nice hypersurfaces. Okay. Now we have the conjecture question, do we know some nice class of hypersurfaces for which this conjecture is true, the one that's written over there on top. Yeah, this was a recent breakthrough of Jingjing Huang in 2020, where he was able to show in dimensions n bigger than equal to 3, he was able to show that whenever your hypersurface has non-vanishing Gaussian curvature, so the first example you would think of is a sphere, but it could also be a paraboloid or anything else, then this heuristic guess that we saw is indeed correct for your delta in the range delta bigger than Q inverse, the range you wanted to prove. I think it's not as visible as I wanted. So he was able to show this. So before this result had only been established in the plane for curves with non-vanishing curvature, Gaussian curvature, non-vanishing curvature, and this was done by Huxley initially by using a determinant method, just no harmonic analysis, and then later his result was improved using some harmonic analysis, but all in the plane. Now this result is a breakthrough because it's a sharp, he is able to get to the sharp range of delta in terms of up to Q inverse, and he's able to show it in all dimensions bigger than equal to 3 for all hypersurfaces non-vanishing Gaussian curvature, which is a big class. So what would it mean in terms of this parameterization that we looked at in the beginning? So remember, our hypersurface is parameterized by this function f, which is a function from r n minus 1 to r. So non-vanishing Gaussian curvature would mean in terms of this function that if you look at the matrix of double derivatives of this function, which is the Hessian of the function, that's an n minus 1 dimensional matrix. This matrix has the determinant of this matrix is uniformly bounded below on your domain. That's what this would mean in terms of the non-vanishing Gaussian curvature. So if this is true, then Huang says that yes, you do have, you do know how your rational point count looks like, and it is delta times q to the power n in this way. And late after this, there was also a result of Schindler and Yamagishi just a couple of years ago, where they also use Huang's result as a black box, and they are able to extend this result to actually manifolds of higher codimension. So not hypersurfaces, but slightly bigger dimension as well. But they need a very strong curvature condition. But that's also something which is known now. Okay, so this is very nice, and we see why curvature is important. And we saw two examples right now, two extremes, right? One where the curvature totally vanishes everywhere and it's a plane, and one where the curvature is never vanishing, nowhere vanishing, right? So but what about something in the middle, or maybe where if we allow the curvature to vanish, but in a very controlled way, maybe at one isolated point. So let's see an example of such a case. So, so now another parameter enters, it's the degree of my curve. So for a natural number d, I define the Fermat curve to be the one which is implicitly parameterized using this function, and it's obvious why it's called the Fermat curve. And this curve, if you draw it, I mean, this is just a curve in the plane, you can draw it, and what you would see is that when x equals, there are 2 points where its curvature vanishes, look, which is when x is 0 and y is 0. And that's when it becomes locally flat. So I will show a picture just in a bit. But what happens is at these points, when x is 1, when y is 0, then the line x equals 1 has an order of contact, this tangent line of order d minus 1. And similarly in the other case. So so these are 2 isolated points where the curvature vanishes up to a certain order. And even in this case, where you have just 3 or 4 points where curvature vanishes, that heuristic fails. And why is that? Because you can again count number of points around the delta neighborhood, and you would see that it's always bounded below by this first term, which we expect, delta times q square, but now a second term as well, which depends on the degree of flatness. So this is kind of like this is how the flatness, local flatness makes itself shown, something like this. So this is delta over q to the power 1 over d. D is the degree of your curve times q square. So now there are 2 terms which compete amongst each other, and you can make a calculation, and you would see that when delta is, so the heuristic we want to prove is for delta bigger than q inverse, but already there is a range between where delta is still bigger than q inverse, but less than this quantity, where it's not the term that the probabilistic term which dominates, but the second term right here which dominates. Meaning in this, there's a range of delta where the heuristic that we want to prove is not true, and that's because of the flatness that we see. And why is that? So the conjecture would fail, and one needs to prove a different theorem, but what should that result be? So what is the geometry behind what's happening here? Where's this term coming from, the second one that we see? So this is what maybe I would like to call in this talk a knapcap type obstruction for this. So let's see a very cartoonish picture of what's going on. So if you draw the Fermat curve, so this is the case when y is 1 and x is 0. That's the point. So you see that if you would have a circle, this would be curved throughout. But now the moment d is bigger than 2, you see this local flatness come in, because at this point the curvature is vanishing totally. So locally your curve looks flat. And what's a good way of measuring flatness in a geometric sense? Well, how easily can you fit this curve inside a box? The flatter something is, the easier it should be to fit it inside a box, meaning the thinner the box you can take. But so that's the measure of flatness, which this picture is trying to show you. So what's happening is that remember, our thickness, so the neighborhood that we are interested in around our curve is of size delta over q, right? So this is delta over q, and then my question is, okay, if I have a thickness of length delta over q around my curve, how long is a piece of the curve that I can fit in this box of thickness delta over q around this point? And it turns out that geometrically it depends upon again the degree of the curve that you have, and you have to do some Taylor expansion and see it. But maybe for this purpose of the talk, take my word for it. Basically, the length here that you can fit in is something like delta over q to the power 1 over d, where d was the degree of the curve. So again, let's carefully think. So delta over q is a small quantity. So delta over q to the power 1 over d, so 1 over d is less than 1, would be bigger, way bigger scale than delta over q. So because things are flat, so you can put more of your curve inside this box of length delta over q. And at this scale of delta over q to the power 1 over d, at this scale, your curve pretty much looks like the A. Basically, it's a line almost at that, if you zoom into that scale. And therefore, you cannot really do anything better than the trivial count in the same sense that we saw earlier in the example of the hyperplane. So what will happen is, at this scale, you cannot really do anything better, and you will catch as many points as it allowed by the volume of this cap that you cut. So you just, what's the volume over here? So the length of this cap, I mean, this is in one dimension, so this is just delta over q to the power 1 over d. If you're in n minus 1 dimension, you raise it to the power n minus 1. So that's the volume of the cap. And the proportion of points, that's the proportion of points that you would get out of the total q to the power n. And that's where this expression is coming from. So q to the power n is what you would have gotten if you had counted everything. And because of the geometry, what happens is you cut the same number of points as the volume of the cap, which is delta over q to the power n minus 1 over d. And that was exactly the term that you saw earlier. There n minus 1 was 1. So now that is why, because of these, so now you have a probabilistic term which competes where things, at least in the case when you have non-vanishing curvature, but around the point where you have a non-vanishing curvature is the second term, around the point where the curvature does vanish is the second NAPCAP type term which comes in. And the question is, when is this all, and when does one term dominate over the other, or so on. So that's a bit about the geometry that I wanted to say, and this was an example for a curve in the plane. So when Nicholas and I wanted to study this problem in higher dimensions, what we wanted was another example in higher dimensions for hypersurfaces where the curvature does vanish in a controlled way at exactly one point. So the example of hypersurfaces that we consider are hypersurfaces which are parameterized by a homogeneous function of a degree d, and so it's for the homogeneous function of degree d, the Hessian for sure vanishes at the origin, and we are considering the class of functions where the Hessian just vanishes at the origin. Okay, what is a good class over here? For example, in higher dimensions, you have x and the length of x raised to the power 4. That would be an example, or more generally, x and the length of x raised to the power d. So this would be a homogeneous function of degree d. And the idea is this should also look flat. So if you plot some of the pictures, you do see this flatness come in. So for example, d equals 4, this is the origin, and you see that your curve is flat. If d were 2, this would just be a paraboloid, which is completely curved. But the higher the d, the more the flatness. And don't worry about these kinks. They're not there. The space is the hypersurface is really smooth. I just cut the graph off at some point. So that's one. And for example, if you take d equals 40, which is like a very, very high degree, you really see the flatness come into the hypersurface around the origin. And so things like the idea is as d goes to infinity, your surface becomes infinitely flat, and that's the hyperplane case. Okay, so this was the class of hypersurfaces that we looked at. And for this class of hypersurfaces, we had this heuristic guess that there should be these two terms that should matter. And we are able to show that this upper bound is actually true for this class of hypersurfaces that we looked at. But you do have to put not just the probabilistic main term, but this flat term as well. So what's that term? So suppose we are in dimensions bigger than equal to 3, which was the same case as Huang's for non-vanishing Gaussian curvature case. And suppose we have a function, a hypersurface, which is parameterized by a function f, which is homogeneous of degree d, which can be bigger than equal to 2, and which is smooth away from the origin. And the important thing is, suppose, so we know that the Hessian of this function will vanish at the origin because it's the determinant of the Hessian is a homogeneous function polynomial as well. But our assumption is that that's the only place where the Hessian of my function vanishes. Then the upper bound for the number of rational points in a delta neighborhood of denominator size q is indeed determined by these two terms. The first term, which is the probabilistic term, which comes in regime when there was curvature, And the second one, which comes because of the geometry around this point where there's flatness, or the local flatness. And again, the implicit constants depend on the manifold and dimension degree, but the point is they're independent of delta in Q. So that's the result that I would like to talk about in the rest of the talk today.
I have a small question here. Why you assume always dimension here means integer, right? In this result, you have written that n belongs to Z.
Bigger equal to 3.
So that, oh, it's bigger than equal to 3. Okay, oh, sorry.
Yeah. So I mean, well, there's a question there that the plane. Sorry.
Yeah, n bigger than equal to 3. Okay. Sorry.
So it's same. It's the same result which. I mean, it was the same regime which is there for the non-vanishing Gaussian case for Huang. But
no. Sorry. Yeah. I got it. Okay.
It's sort of, I would say maybe a non-standard notation. Okay. So this is the result I would talk about, and we would get to how the harmonic analysis is coming in. But before that, I would like to discuss a bit of a consequence of this result. So you see now these two terms which are there, and and another important thing I want to highlight over here is that our result is also true in this sharp range of delta. So the one that you expect, which is Q inverse up to Q inverse. But in this range now, what you can do is you can play this game again. There's a certain range of delta in which the first term dominates for bigger deltas, and there's a certain range of delta in which the second term dominates. And you can figure out what that range is. That will depend obviously on n and d as well, and q for delta. But if your degree d of flatness is small enough, actually for the certain range of this degree, where actually the first term will always dominate. So you try to put these terms together and see what that range for delta is, and if this covers Q inverse. And yes, it does turn out that when D is small as compared to your dimension, so D is the degree of flatness, N is the dimension, and if your D is less than or equal to 2 times N minus 1, then indeed it's always the first term which dominates in this range of delta. So in that case, for small enough degrees of flatness, actually the probabilistic guess is the correct one, which is very nice. Like these are examples of surfaces where you do have curvature vanishing at these isolated points, but the probabilistic guess is still true, the same as the Gaussian curvature case. However, the moment your dimension, the degree of your surface crosses this barrier of 2 times n minus 1, then the second term will dominate in a certain range of delta. And so there you see that the theory diverges from the conjecture that was initially there. So that's interesting. And then therefore you see when these two, that's the non-vanishing Gaussian curvature case. In that case, this condition is always true. And that's what you see, that is why this guess is always true. When these two, which is the non-vanishing Gaussian curvature case, like the paraboloid, but the moment it becomes strictly greater than 2, you can see some divergence happening depending on the size of the dimension. Okay, so that's what I wanted to talk about. I mean, just the heuristic of the result, and also the other thing was right, and also the geometry. But now I promised you that you would see some oscillatory integrals or harmonic analysis come in. So let's talk a bit about how to reframe this problem in terms of harmonic analysis, in terms of oscillation, and how that might help us in our in this kind of problem. So let's come back to our counting function. And again, I have mentioned the definition again. There were 3 conditions, right? So we would be using oscillatory integrals, which means we'll be doing a lot of integration by parts. So the first step is to make everything smooth. Right now, all these conditions are sharp, right? Like, the first step would be to just introduce smooth bump functions to capture these conditions. So the first condition is just saying that the size of my numerator should be less than Q, or P over Q, the size of P over Q should be less than 1. So I introduce a smooth bump function W, which pretty much lives in the, which is maybe exactly 1 in the unit ball of radius 1 in the unit ball, and is compactly supported in a slightly bigger ball. And that will take care of the first condition. For the second one is to capture the condition that the size of my denominator should be roughly of size big Q dialectically. So you take another smooth function omega, which now lives in an annulus, say an annulus of size 1/2 to 4. And then there, this would capture the second condition. So these are just like some standard things which make us more comfortable as analysts. But now, again, the third condition is the most crucial one. And currently, what is that third condition saying? If I want to reframe it in terms of a characteristic function of a set, I am measuring when is my argument, which is Q times F over P over Q, right? This is my argument. When is the distance of the nearest integer of this argument less than delta? So that's pretty much the set I'm after. The set of all thetas where the distance of the nearest integer is less than delta, and this function should be 1 only if my argument lies in that set. So that's the characteristic function of the set that I'm looking at. And I want to estimate this characteristic function also by means of a nice function, not the characteristic function, but something else. And what I want to estimate is by, I mean, you have different choices, but that is how the oscillation will enter the picture. I would like to use the Feher kernel, which is an exponential sum, to capture this condition and estimate the characteristic function of the set. So what is the Feher kernel, which a harmonic analyst...
Rajula, just 1 second. Can you correct that previous slide? Okay, so this is really... okay, so that norm of our this symbol, which is you are written QFP P by Q R by Z. This is something like MFP minus M minimum of this. What is that expression?
Right. So the distance to the nearest integer. Like torus, the norm on the torus. Like,
and what is the exact definition of that?
So that is
norm of theta R by Z. Norm of theta R by Z.
Norm of theta R
by Z. This indicates
to be minimum of over all integers m in Z theta minus n. So you take basically the distance to the nearest. Okay. Yeah. So like what would be? I mean, it's a if you look at periods, then where would it be on the torus?
Yeah, I understand.
Yeah, exactly. So once you have this, now this function. I want to basically dominate this characteristic function of the set by some other function, which I know would be, roughly constant on this set, on exactly the set, and then falls off very rapidly. And the function that I would be using would be the Feher kernel, because that's what will introduce this oscillation. So it's this uncertainty, that by the uncertainty principle, that's where the oscillation comes in. And to measure it, you can measure it by a superposition of waves of a certain frequency. And that's pretty much the Feher kernel. So what is happening here? So the Feher kernel is, I will take this exponential sum up to frequencies big J. And big J is roughly like delta inverse. So what was delta? Delta was the size of this uncertainty here that I wanted to measure. So by the uncertainty principle, the exponential sums or the waves up to which I have to take the superposition to measure this should be roughly the inverse. So it's delta inverse. And I mean, there's some coefficients here, but don't worry about that. They are like, they are bound by 1. Then there's also, it's normalized. So you have a 1 over J as well, which would be important. So
sorry,
if you do
actually,
that,
sorry.
Yeah.
Actually, I missed something. Actually, can you go back to previous slide? Actually, okay. So actually, I understood that this thing NF delta Q you are estimating by this thing. Okay, W Q by means. So how you are getting this thing? Actually, that so third thing is okay. So W is
so basically, I mean, I'm being a bit, I'm not exactly. So basically, what is happening is this is just a unit, the characteristic function of the unit sphere, right? So the condition P infinity is that it's the characteristic function of the unit sphere evaluated at P over Q.
Okay.
All I'm doing is I'm just dominating this sharp cutoff by a smooth weight.
Yeah, that W is okay. Then omega?
Omega would be, so Q is between, big small q between big Q and 2Q, right? So if you have a omega, which is, like 1 between in the interval 1 to 2,
Yeah.
only lives in. So it's that. So that's pretty much what is happening.
Okay.
And right now I'm just talking about upper bounds. You can do that, and then if you're careful, you can also.
Yeah. Thank you.
Okay. So no, it's a bit of notation. So yeah, but essentially the point is like you just smooth everything out. Right. So you have this Feher kernel and the sum of exponential. This is an exponential sum, and using this uncertainty principle idea, and I'll show you a picture in just a bit, which hopefully makes things clearer. You can dominate this characteristic function by this exponential sum. Okay. Going up to frequencies big J. Big J is like delta inverse. And this is your argument, Q times f of p over Q over here. So when you, and the picture that you should have in mind is something like this. So, okay, this picture of the Feher kernel is not exactly the same, because what I have there's 1 over J as well. But if you just look at the argument, this is how the Feher kernel looks like, right? So the more the frequencies you take, the more the cancellation, and so the more concentrated the set on which it essentially lives, and then it falls off rapidly. And roughly the idea is that if I want to measure an interval which is only of size delta, basically take frequencies of length about delta inverse up to delta inverse, there'll be a lot of cancellation. So on an interval of your size delta, this superposition will be roughly constant, which is what you want. But beyond that, will fall off rapidly. It's not compactly supported, but the fall is very, very rapid. So you can dominate it, the characteristic function. And I mean, this one keeps on increasing. The peaks keep on increasing. But if you then normalize it by 1 over J, which is delta, will pretty much be a nice upper bound for your indicator function. So you are using the oscillation to actually capture that uncertainty or that neighborhood of your function. But once you do that, you have bounded your original Poynting count by this smoothened version with this exponential sum. So again, W is like the smooth weight, which lives on roughly on the cube, n minus 1 dimension cube. And then omega is another function. And now you also have a sum of these exponentials up to frequencies big J. Big J is like delta inverse. Now the idea is I want to use the oscillation, this cancellation, to actually get a nice point count or a nice estimate for this number of rational points. But oscillation, there's one case where there is no oscillation, and that's when J equals 0, right? Because there is no exponential sum, you only just count everything out. So let's first isolate that term out. So there's a sum in J, but I only isolate the term with J equals 0, because I know I'm not going to get any oscillation there. And when you do that, the sum in J is not there anymore, because you're looking at J equals 0, and then you carry out the sum in all these smooth parameters. And again, I mean, when you sum up in these lattice points, n minus 1 dimensional lattice points, and then the denominator of size q, you get q to the power n. But now you have this 1 over J as well, because of the normalization of your Feher kernel, which is like delta. So that's why you get delta times q to the power n when there's no oscillation. That's exactly the term that I expect, the probabilistic term. So in this Fourier analytic way, you really see how the sum pops out. When there's no oscillation, you get the main term, and the rest, there should be oscillation and there should be some cancellation, which should make things, the rest like lower. Which should make the rest of the terms not matter. The question is how to exclude the oscillation. Okay, so now that we've isolated the case where there is no oscillation, for the rest of the sums where J is not 0, let's use Poisson summation in this lattice here, n minus 1 dimensional lattice. So what Poisson summation will do is it will convert this exponential sum into oscillatory integrals, where we can start using these techniques. So let's do that. Again, this is what we had come to. This was the point count. For non-zero frequencies, I use Poisson summation in this inner sum that you see over this lattice, n minus 1 dimensional lattice. Okay, so you have this inner sum over here, and Poisson summation says that the left hand side, the sum over this integers lattice to be equal to another sum over the integer lattice of the Fourier transform of the function that you have over here. And all I've done is I've written explicitly down the definition of the Fourier transform of this function. That's why you see this integral over here. So on the left side, you have this sum. On the right hand side, another sum. Now I call my lattice variable k. And this, what you have over here, is exactly the Fourier transform of this weight. So Wx over q. And then you have this exponential sum, exponential factor, which comes from the sum. And then this minus k dot x comes because I'm taking the Fourier transform and evaluating it at the lattice point k. So this is just writing the Fourier transform. I mean, I'm just using the definition. And let me just say that for me, E of something is always e to the power 2 pi I. Okay, just not get confused. And now I'm getting closer to a case where I can use my oscillatory techniques. So what I do is I will, let me just renormalize things a bit. Right now my weight is not normalized, it's x over q. So I just make a change of variables. And now I have something which I can try to analyze. So you have an oscillatory integral. This is the phase of your oscillatory integral. There's a function f that you started with, but now there's a linear perturbation because I applied Poisson summation. And this is your amplitude, which is a nice smooth function. And the decay that I would expect would be in this parameter, j times q. So if you follow Stein, this is what Stein would call lambda in his oscillatory integral. And the idea now is to exploit decomposition, to exploit this cancellation to get some decay in this factor q times j, so that we can show that the rest of the terms over here, this doesn't contribute that much. It's the first term which dominates. Except, for us, we have to be careful. We know there is a problem point here. Here we will encounter a problem at one point. The point where the Hessian vanishes, which is the origin. But the decay that you get from an oscillatory integral really depends on if the derivatives vanish or not. If the first derivative is vanished, perfect, that's really great. But if the first derivative vanishes and the second does not, you still get some decay by using stationary phase. But right from our assumption, we know that at the origin, the second derivative of my function will vanish. So what do I do to handle that? I do what harmonic analysts always do. We make a dyadic decomposition based on how far you are from the origin. So for that, I will replace my weight by this dyadic partition of unity, which basically, so it's a sum over these scales in L, dyadic scales, and each LP is basically measures how far you are from the origin. So what I've done is I've replaced my weight function by the smooth partition of unity across these analytes around the origin. I mean, they will be dyadic analytes. And now I'm very careful because I know that the closer I get to the origin, the more my curvature degenerates. So I want to do this analysis case by case based on how small my curvature is. Now, what I can do here is, I mean, this is a bit of simple pushing, but something is happening. So you can make a change of variables over here. This factor will pop out 2 to the power negative L because of the change of variables. But so now, again, what that does is your rho is now normalized. So the rho, to get a dyadic partition of unity, I start by taking a function rho which lives around the unit analysis. Then I scale things to approach the origin. But here, once I've scaled things back, I am again away from the origin, where everything is good. That's nice. But what has happened is this factor 2 pi L has now come inside the phase. And now I have to see what that does. Now here I can use my homogeneity assumption on the function. So remember, my assumption is that f is homogeneous of degree d. So this 2 to the power negative LD comes out. And then if I again push around symbols, the main point I want you to focus on is the fact that this negative factor, this damping factor has now come in front of this parameter j times q in your phase. So what that has done is, I mean, the decay that I wanted to exploit in was in j times q. But now, because of this negative factor, the decay gets lower, or like the oscillation gets dampened. So this is how, I mean, by just doing these manipulations, you can really see how the curvature is, how the oscillation degenerates as we get closer and closer to the origin. All right, so maybe I will try to be a bit quicker now. So basically, once I do that, I get this family of oscillatory integrals at each dyadic scale. Now earlier I isolated the 0th frequency because I knew there I will not get oscillation. Now again here there are a lot of scales, an infinite number of scales where I will not get any oscillation. What are those? Those are precisely the scales when L becomes large enough that this factor in front becomes 1, right? Because if it's 1 or less than 1, there is no decay. That's the decay I wanted to use. So the moment your 2 to the power LD becomes bigger than J times Q, let's take their dyadic scales, then you do not have any oscillation. And all you can do is you just estimate your integral in a trivial manner, just like take absolute values. But you are not always lost because you have this nice negative factor in front, which basically measures the volume of where the integral lives. So basically above this scale of L, which is when you have zoomed in too hard into your flat point, that's when you just take a volume sum, a trivial sum of this geometric series. And when you do that, you would see that's exactly how, that's the volume of the nap cap that you started, that was the second term. So again, the second term also emerges when there's no oscillation, but now the new no oscillation is because of the flatness, local flatness. So once L, 2 to the power L becomes bigger than this threshold, depending on the degree, the second term, the flat term emerges. And now, okay, so this was the cost of rescaling, that because for large L, you do not get any oscillation. So now let me just call this oscillatory integral ijkl because it depends on 3 parameters, the frequency parameter j, the lattice point k, and L, which is the scale. And now once I even isolate those scales, so I have the probabilistic main term, the volume, the nap cap term, which comes for higher for once you get closer to the origin. And now you have all that's left is to analyze this sum and prove that this term really is not really that important. It is like an error term, okay, of the magnitude that you expect is q to the power n minus 1, maybe with an epsilon of room. And now the game begins of estimating these oscillatory integrals, because now this is the regime where you have some oscillation. Now there are 2 regimes which are important. One is the non-stationary case, meaning your phase function is non-stationary. It does not have any critical point, or in other words, its gradient does not vanish. Because in that case, you can do as much integration by parts as you want and get as much decay as you want, and things will be great. So that's good. That's a non-stationary case. But there is also the stationary case when the gradient of the phase function that you have over here does vanish. And that gives you the critical point associated to this phase. Let's call that xjkl because it depends on these 3 parameters. In this case, remember now our rho lives away from the origin, which is where I can actually do, where I know the curvature does not vanish. When curvature does not vanish, even if the gradient does, I know I can do stationary phase expansion. So if you're not familiar with it, that's basically a technique where you still get some decay because of the second curvature non-vanishing, the second derivative condition. But this decay is limited. It's not as much as you want by doing integration by parts. You get a certain amount of fixed decay in these parameters depending on your dimension. So now it's really important to be able to precisely estimate how many critical points I will have. Because as the oscillatory integrals runs through these parameters jkl, I will have this family of critical points. So, and I know I only get a certain limited decay for these points. So I need to be able to precisely be able to count the family of these points. And just like that, after doing all of this, we have arrived at a dual counting problem. We remember, so it turns out that when we actually start analyzing these critical points, and it's not trivial, it really needs to be seen. You need to do the stationary phase expansion and see that these critical points that you see actually again turn out to be rational points, but now the role of Q and delta is interchanged. These are rational points whose denominator is of size big J, and this distance and at a distance of Q inverse from a dual hypersurface, which is actually parameterized by the Legendre dual of F. So this is something which is very nice, and if I just tell it to you like this, which is what I'm doing, it sounds very mysterious, but when you do the stationary phase, it's natural, but yeah, it is something which takes work to see, and that's a really nice thing. So what has happened is, when you actually do the stationary phase and you start counting your rational points, you you can convert it into a dual counting problem, where now you are counting rational points around a dual hypersurface, which is parameterized by the Legendre dual of your original function f. And now you might ask me, and as I say, that the roles of delta and q are now switched. So the size of the denominator is now delta inverse, and the distance is now q inverse from the manifold. So now you might ask that, okay, but what has happened really? I mean, I just started with a counting problem. I went to all this trouble, introduce oscillatory integrals, and I've again ended up with a dual counting problem. What's the point? Well, the point is you applied stationary phase, which is a big tool in between. You get a lot of decay now. So now when you're counting your rational point in this dual setting, what you're doing is you are actually counting it with decay, which should give you something better. You're not really in the original setup anymore because of the decay from the stationary phase. So, but let's talk a bit about the geometry of this dual surface. So if your original surface has non-vanishing Gaussian curvature, then the dual will also have a non-vanishing Gaussian curvature. So in Huang's case, he again ended up in the same situation geometrically, and you repeat the argument again. However, the moment you go bigger than 2, which is when things become flat, then a new phenomenon starts to happen. So your d is bigger than 2, it turns out that your dual function will also be homogeneous, but of degree d prime, and d prime will be the Holder dual exponent of d. So meaning, for example, if you started with a function which is homogeneous of degree 4, your new dual surface, after doing all of this, would be something which is homogeneous of degree 4/3. So the original one was flat, the new one starts looking rough. So the moment d is bigger than 2, d prime is less than 2. And when d prime is less than 2, that's something which starts getting rougher. And the scaling turns different as well. So the problem really changes. So for example, as I say, if you look at a non-vanishing Gaussian curvature case, your dual, both your original surface and the dual surface will look this way. But if you start with degree d equals 4, so this is flat, its dual, you see, starts becoming rough at the origin. This is d prime is 4/3. And more extreme, if you started with a degree which is 40, so flat, you see it really starts looking very rough at the origin. So now what you have to do is you really need to analyze 2 different cases, which is totally not present, this geometry in the non-vanishing Gaussian curvature case. So as I said before, the point of all this entire exercise of coming to the dual was now you can bound the original rational point count by a dual point count, but with this weight attached, okay, which is the decay from the stationary phase. And the idea now is to build upon this. You start with a trivial point count for your dual surface, and you utilize all this machinery to obtain something better for your original surface. But the point is the process of taking dual is an involution. So you take dual once, you get to a flat surface, then you take dual, you get a dual, but if you take the dual of the dual, you return back to your original functions. There's a ping pong, but what that means is you take a trivial bond for your dual surface, get something better for your original function. Now you apply the same process, but now use the better bound for your original function to get something even better for your dual function. And you keep doing that, so you keep pulling each other by its straps, and it turns out you can keep doing it till you actually get an estimate, which is like the sharp, which I'm not really saying how that is, but that's pretty much the idea. And it's an amazing idea. I mean, it's nice that it works and it can make your error term smaller. The amazing thing is that it actually leads you to the sharp estimate. And what is very important in this bootstrapping argument, I'll not go much into details now, is like you actually need to very delicately induct on the delta scales in each step, which you see from the machinery, which for us is very complicated because you have these 3 terms floating around: the error term, the probabilistic term, and the flat term. So you really need to be very work a bit to see where how to do this induction. But that's the idea, and it really gives you nice estimates. So I think I've already exceeded my limit, so let me just end quickly. So so this was very nice, and we were able to use all of these ideas to actually show that even if curvature vanishes at some points, you do still get this nice estimate. But of course, it's a certain class of functions that we took. You can ask so many questions. For example, what about homogeneous functions of degree less than 1, or even more general functions For example, if the curvature does not vanishes at isolated points, but for a surface, a low dimensional variety, that would lead to an entire different beast of problems, and one might need even more techniques from oscillatory integrals to actually do that. And yeah, I mean, all of this is in dimensions bigger than equal to 3. In the planar case, somehow harmonic analysis does not give as sharp results, but we do have some ongoing work where we are able to say something nice in this case as well. But that's all I would like to talk about, and thank you so much for your attention.
So, any question from the audience?
Yeah, sorry for going a bit over.
No, that's okay. I can ask some questions, okay? So
Yeah,
I will ask
sure.
otherwise. So the thing is, I just wanted to know that, see, if f is suppose norm x to the power p,
Yeah.
fx. So is it true that dual of f is norm x to the power p prime?
Yeah. That's what. If you take it of this form.
You only said about this homogeneous thing.
But like x norm x to the power p would be homogeneous, right? Of degree.
Yeah.
Right. So yeah, in that case, it's true.
So it will be norm x to the power p prime, right?
Yeah, exactly. And that's why this duality comes in between flat and rough cases.
So I have to just, can you go back to the thing where you dominated the things by phasor kernel, this one indicator?
That's like an important step, yeah.
Yeah, that actually I somehow couldn't understand or something I missed. Can you explain that thing?
This one?
Yeah.
So you are asking specifically about the phasor kernel, right?
How did you dominate by that phasor kernel?
Yes. So, I mean, I can, there's of course a calculation you can do, but let me first show you the picture again and go from there. So this is the phasor kernel.
Okay, no, go back to the definition first, the previous page, sorry.
Yeah. So, okay, what's happening is, I mean, I don't want to do all the calculations.
So can you go back to the previous page?
Previous page, I mean, here there's no, right.
Oh, yeah. This one. Okay, you have written that. Okay.
Yeah. Here. So basically what is happening is actually you can write it in a closed form. So this thing will be actually something like, I think I'm sine pi j theta over sine pi theta square, something like this, right?
Yeah.
So now if the distance to the nearest integer of your theta, and then there's a j here as well, okay? So there's a j. Right. So if your distance to the nearest integer is less than equal to j, something like this, then basically what's happening is that you can j inverse. Sorry, this is actually dominated by some constant, something pi square or something like that. You can actually prove that estimate. So what's happening is that the moment your theta is in the set, you know that this function that you have is bounded below. So you can use it up to constants to estimate all thetas in this set. That's the idea pretty much. So, and the picture is pretty much here. Like you squish it down, but the thing is, up to this width, this is pretty much like roughly constant. And I mean, if you don't like the phasor kernel, what you could have also done is, do everything smoothly. So you could have started by taking a function which is compactly supported, and essentially the idea is of a smooth function compactly supported. If you take its Fourier transform, if the function is compactly supported in interval of length delta, its Fourier transform essentially is constant on an interval of length delta inverse. And that's pretty much what's happening. So you can also do that, but it's pretty much on the uncertainty principle.
Okay, so I have one more question. The thing is, you have really said that if delta is greater than 1 by q, so in ideal cases, it is really behave like q to the power n minus 1 or something.
Yeah.
You are giving a sort of
delta is less than.
Oh, delta is less than.
Yeah.
Okay. So the thing is, can you do better this thing q to the power n minus?
So I think for this class of hypersurfaces you cannot. I mean, which is already like the first starting point, because already you have examples like hypersurfaces. where you cannot do better. Like the sphere, you will count that many points on the sphere. However, a slightly different result, which I just very briefly mentioned, was when I said that Huang proved this result in this sharp range, where's this thing gone? There's also this result of Shinra-Yamagishi, which is not for hypersurfaces, but for surfaces of slightly higher codimension, which with also very strong curvature conditions. So now you will have not just one function, but maybe two, you have a higher codimension, so you have like d many or r many functions for each codimension. And then if you take any linear combination of the Hessians, that has to have a determinant bounded below. So there's some very strong curvature condition on their manifolds. And for that class of manifolds, they are actually able to go beyond this conjecture. So in that case, the conjecture would not be Q inverse. The conjecture is actually delta bigger than Q to the power negative 1 over R, where R is a codimension. Here I was talking about hypersurfaces, so it was just one. But in general, for a higher codimension surface, this would be the conjecture. So they do consider hypersurfaces, manifolds with high codimension, and they are able to go beyond this. So it does seem like, for certain, maybe not for hypersurfaces, but for other manifolds, it might be possible to go beyond the conjecture. And in fact, I'm actually working on something like this. And extending the result where I think I'm able to show that you can go even beyond this conjecture, even what they prove. So that would be great. But yeah, that's a good question.
Actually, I have one more probably question. The thing is, so that the question you have started, it looks number theoretic.
Yeah.
But the thing is, do you know the motivation of studying this kind of problem?
That's a good question. People are always interested in this lattice point counting. This is not lattice point, this is rational point counting. So here there's more of an averaging involved in the denominator. So sometimes it's like, one motivation could be, okay, maybe saying something about actually counting lattice points is hard, but rational point count is easier, so let's study that. But also, if you get nice results on this rational point counting, you also have applications in Diophantine approximation. So, for example, there's this Khinchin's theorem, which says that, okay, what is the size of what is the dimension of the set of numbers, which can be approximated in some nice sense by infinitely many rational points. And you can ask something similar for hypersurfaces. And then if you have this kind of sharp point count, it immediately applies a corollary, some genetic results for those manifolds as well, which is, a closer related problem, but it's more about approximation by something. So yeah, that's also one of the reasons people might care about it, yeah.
Okay, so are there any questions from audience?
Okay, so I have one question. Hi, I'm Kalachand.
Hi.
So, okay, so if the hypersurface is cone, then
yes,
is there anything known about it?
That is such a nice question. One would think that one could do something, right? Or even like one could, because cone, we know one curvature vanishes, but then
Yes.
the others, maybe we can project down and then just count trivially in one direction and say something. And that is what, but it came as a surprise to me that that doesn't work. It doesn't give you what you might expect, even with one non-vanishing curvature. So as far as I know, even in these cases, what exactly the conjecture should be for non-vanishing curvature and what you can say very little is known. That's a good question. Yeah.
Okay, thank you.
Yeah, thanks for that.
Any other question from the audience? Yeah, Rajula, actually your talk is recorded,
Okay.
and will it be okay if you will post in YouTube?
Yeah, that's okay. Thanks for
That's
asking.
okay.
Yeah.
Yeah. So if there
Maybe
are no more questions, let us.
Maybe there's something I wanted to quickly say. Maybe you guys already know. Let me just stop sharing. Maybe. I briefly talked about it. So there are these two summer schools in Bonn in July. One is about the maximal operators, and the other is about. Okay, now I can't. I don't know how to stop sharing. And it would be great if, it's in July and the deadline to apply is like another 2 days. I think Professor Tangavalu sent an email on disk about this. So if you can apply for it, please do consider. And if you can come, it would be great. Yeah. One topic is on maximal operators and the other is on oscillatory integrals.
Okay, so let us unmute and thank the speaker then. Yeah.
Thank you.
Oh, Apurva, you are here. Yeah. So I don't have to call you. Thank you.